which gets us into chapter 3, okay, or the beginning of chapter 3. Right? And really the big aspect that I want to drive home out of this is qualitative versus quantitative. Right? When we move into science, most people think of science and they match to which of those two terms? Do you know that yet?
Yep.
Okay, which term do you typically associate with science?
The science, one of these things, quantitative.
Okay, so what are you cranking through in your head when you're qual?
I do qual and quantity, like quality and quantity. That's what I do.
Qual for quality.
Yeah.
How good did that food taste? Okay, it's kind of a personal observation, right? Quant for quantitative. I ate 4 pizzas slices. Okay, 4 pizzas. Okay, so the quantitative gets down into our numerics. Okay, the numbers associated with those. Our qualitative is kind of an observation.
It's based on perceptions.
Idea.
Yeah, see, this is why it's nice being with somebody who teaches English, because they can actually use better words than me. Perceptions. Okay? Because you can clearly tell where my training has put me. I've been put into the quantitative category. I deal with numbers. Okay? So does that mean when we're doing science, the only thing we're concerned about is the quantitative?
No.
No. Okay? I went into the experiment, I mixed some water and some salt, and it blew up. How many of you have mixed water and salt?
Every day.
Okay. How many times when you've mixed water and salt has it blown up? Why did it explode? Yeah, a tablespoon.
Probably wasn't water then.
Ooh, interesting. It probably wasn't water. May not have been salt. Okay. But if my observations for that experiment were it was water and salt, I have no idea what happened. But what if I added into my observations of doing that experiment that I added 50 milliliters of water and 2 grams of salt? Well, that changes everything now, right?
Oh, yeah. Yes. Measurements are important.
I now have measurements, but have you changed the amount of salt you've added to water before? Did it ever explode?
No.
Okay, so something's still missing here. What also needs to show up in my observations? That would then even go to the item, and I would argue we don't even need to look at the item yet, because I still think it's water.
You need label.
A label could still say it's water.
You like test that it's water.
I mixed a black liquid that was labeled water with an orange solid that was labeled salt. Then it exploded. Was water supposed to be a black liquid? No. By adding that little bit of qualitative information, I now have the ability to go back and troubleshoot and say, whoops, somebody mislabeled something somewhere. We need to clean up that experiment and adjust those conditions. So the qualitative and the quantitative observations, okay, go hand in hand. We can't just ignore one to favor the other. Does that make sense? Let's look back at the quantitative. Notice in the quantitative we've just got numbers written down. Okay, there are 2. What am I talking about?
2 substances you mix together.
Okay, I like the 2 substances you mix together, and then the part that I really liked in that was what was mumbled right at the end. I don't know. Yeah, good point. The quantitative observation is not just numbers. It is also the substance. What are we measuring? The object, okay? Also known as a unit. So when we go through to make measurements and observations, qualitative can be nice. I can say it looks pink, it looks purple, it looks mauve. I think we decided it was actually green. I don't remember. Okay.
Or the salt. Black and orange.
No, just colors in general.
Oh, okay.
Quantitative, I can go back and I can specify how much of that mauve species there was. Okay? So it's a question of including both of those when I go through any experiment, because it will allow me to troubleshoot later on, and it will also allow me to run calculations off of those numbers if I need to later on as well. So both are important. Okay? So let's make some qualitative observations. So really we're thinking about kind of historical aspects. How does chemistry start? Where did it come from? How do we decide we even had matter? So our big qualitative observations. Probably the most important species as far as chemistry is concerned, okay, and really science, is something that we're all familiar with. What is roughly 70–80% composition of life? Water. Okay, the species H2O. And it is an interesting species for one particular, or at least one particular observation.
Are all three stages?
I can have varying states for that same object or that same thing. I can take solid ice and I can add a little bit of heat and turn it into a liquid. And if I add a little bit more heat, I can turn it into a gas. So I can transition between different apparent physical states. So we can then go through and classify our matter according to the phases. Once we've got these classifications, we want to come up with ways that we can measure or observe these. How could we compare solids, liquids, and gases to each other?
Density levels.
Okay, we could look at different densities. Okay, we could look at shape, volume, compressibility, the big things that I think your textbook likes to address. Okay. What happens with the shape of our solids, our liquids, or our gases? Are they the same? No. How about volumes?
Depends on what you're dealing with.
Okay, it depends on what you're dealing with. Compressibility
Again, depends on what you're dealing with.
depends on which phases you're looking at. So let's see if we can come up with some comparisons between these. The gas is one I seem to find the easiest. When we look at a gas, what happens to the compressibility? Do we have the ability to compress?
Yes.
Yes. How about volume?
Fills its container, whatever it's in.
Okay. It'll fill the container that it's in, which is really kind of shape. Is that highly mutable? Okay. It'll change to its container. That says container. I just ran out of space. How about liquids?
Next to nothing compressibility.
Okay. When we think about our liquids and we try to compress a liquid, they really don't compress much.
What did the textbook, what was the word that it used to describe that?
I don't know.
Negligible? Yeah.
Negligible is a good
Yeah,
one.
that was the word that it used.
Come on, English teacher.
Nope.
Nope.
Don't worry about it. Volume.
It's fast.
I think it's at the same point.
It'll change to its container with like a limit of how much
So-
liquid there is.
Our shape and volume end up starting to get related. And I'm hearing people, well, the volume of the liquid will change depending on the container. Is its volume really changing?
The
No,
volume
the
remains the
liquid is
same.
changing.
It'll be no. It'll stay the same.
And it'll take the shape of whatever container it's in.
To its volume. Okay. So I can change the shape of the container, and the volume will fill that shape. Okay, but it's never going to fill beyond the volume of the liquid. Kind of make sense? Solids. Compressibility. I think that's the easiest one. You and negligible, huh? Zero compressibility. Volume. Okay. Static, why not? Also known as stays the same. Okay. And our shape? Okay. The shape, I would argue, is then also going to be very static. Yes, we can then remove it, okay, and force it into a new shape, but then it stays in that new shape. Whereas our liquids will fill to the shape of the container. Okay, so they are constantly moving around. So how could we then take this information and turn it into some pictures? Because I don't remember if I've got that picture right next, so let's just go ahead and draw some. Let's say this is my water molecule, a happy little circle. So I'll put a happy little circle for a liquid, solid, and a gas. If I'm looking at any one of those phases, is it likely that I'm only looking at a single particle? No, I've got a bunch of particles. Okay. Where are those bunch of particles relative to each other for the solid, the liquid, or the gas?
Solid, they're closer together.
Okay. Remember that compressibility aspect we talked about? Okay. We said it can't compress. Why can't it compress? There is hardly any space in between those, which means we can't compress them closer because they now bump up against each other. Okay. What about liquids?
Slight compression or...
What happens to that space between?
They move around.
It gets a little bit bigger. It's also a little bit less organized. So sometimes they'll get a little closer. Sometimes they'll be a little bit further apart. But for the most part, they're all pretty close.
Because there's more energy, collisions.
If we think about how we transition between the solid to the liquid, how did we do that?
Applied heat.
We applied heat.
Energy.
We added energy to it. What happens when you get more energy?
It increases collisions.
I didn't ask about
Speed
particles. I asked what
reaction.
what happens to you personally when you get more energy.
Move.
You have a little sibling or something, and you feed them a bunch of sugar.
I thought that was an urban myth.
They become more active and run around. We can look at observations and myths later. Okay.
Just for a few minutes before they crash.
They will then run around and expend that energy potentially. Okay? So the more energy we have, the more motion we have, which then means we start to become more disorganized. What then happens is we add even more energy. We now completely allow complete free motion, and now the distances between become massive, particularly in comparison to the size of our individual molecules. Okay? That's why when we look at the gas, we can compress it. Why can we compress it?
We have a lot more space in the water.
There's a lot of empty space that I can then close down with those individual particles. Okay? In the solids, those particles are actually holding on to each other. Okay? Which is why when we look at their shape and their volumes, they hold. But when we move to the gas, they aren't touching each other, which means they can't hold on to each other, which means when we put them in a container, where do the particles go? Everywhere. They fill the entire volume. Kind of make sense? So what we're looking at is kind of some broad observations and then trying to come up with a model to represent it with these silly little circles. Okay? I always hate how it changes the colors. Oh, that one looks better. So look at that screen. That screen sucks. We look at this screen. We've got the little lines connecting these things. So we've got our matter, right, which has solids, liquids, and gases. Those are our primary categories, right, for our matter. But then what we can do is divide matter into two separate categories: mixtures and pure substances. Okay? Mixtures are spatially linked. Okay? That means you are next to the people around you. You are next to the chair. Okay? Pure substances are chemically linked. Every part of you is chemically bound to you. We can't just like, whoop, there goes your hand. Okay? It is chemically linked and part of your character. Each of those can then further subdivide into two other categories. These things known as heterogeneous and homogeneous mixtures, or compounds versus elements when we look at our pure substances. Okay? So heterogeneous and homogeneous. We've got a couple definitions up there, so let's switch it up. What definitions do you have? What definition do you have for heterogeneous or homogeneous?
Like a C or something, like a concentrate or something, or
Suspensions?
suspension, yeah.
Okay, so what we're saying with suspension is now an example of one of those. I can work with that. Let's work with examples. Maybe examples are easier. Where is a suspension? Is that heterogeneous or homogeneous? How many people know what suspensions are?
Heterogeneous.
What's that? Okay, we have a heterogeneous because we see a physical separation.
Isn't homo one, heteros two? Or more?
What was I writing? Suspension.
Is this like regular twice compared to side?
Right? I heard a better one, oil and vinegar. I think more people have seen oil and vinegar.
When you say suspension, are you talking about like the part of the car?
No. That's why the oil and the vinegar one. That's why I asked about suspension. And everybody's like, oh yeah, I totally started knowing that and started shouting out examples. So let's get rid of suspension and keep with our oil and vinegar. Because I think the oil and vinegar works pretty well as a suspension. Right? I heard 2 versus 1, which was then very quickly changed to what? 1, and then I believe you were then saying 2 or more. 2 or more what? 1 what? I ate 4. Yeah, what?
Substance.
Okay. What is that substance? 1 what for homogeneous? 2 what for heterogeneous? So if I have 1 substance, I'm going to have a mixture?
No, it's going to be a pure substance. It's going to be an element.
That would then be a pure substance. So I can't have 1 substance.
No.
One mixture.
Just one evenly.
So what is our unit on that 1?
Density?
No. 1 mixture?
One love?
Have we talked about something about matter? Another way to classify matter? We haven't even got to compounds yet. What did we talk about on the previous slide?
What is just one state of matter together?
There was not 1 state of matter. What? Solid, liquid, and gas. Mixtures, if we're looking at heterogeneous versus homogeneous, a homogeneous is 1, whoa, that's an eraser, phase. It is all solid. It is all liquid. It is all gas. Heterogeneous is 2 or more phases. Okay. You might say, well, that sounds pretty good. We got a nice, easy, quantifiable way to compare that. What phase is oil?
Liquid.
What phase is vinegar? So how many phases would I have if I mixed oil and vinegar?
You all put like basil in it and stuff too.
I would then just have 1 phase. It's all liquid. But do those phases interact with each other? No. So I can have multiple phases or multiple of the same phase, but if they don't evenly mix, that's heterogeneous. If I take multiple phases and they all mix with each other, that's homogeneous. Where might we have a homogeneous mixture? Air. Everybody picks air. I don't know why everybody picks air. How many of you can see air?
Always.
I mean, it's not wrong. It is a homogeneous system. But that's a really hard one to nail down, because we can't see that. Let's pick something that we can see. Water? Okay. Water in and of itself is a single substance.
Steel?
What if you drink that water and you're like, oof, that's salty? That would be salt water. Is salt water does salt water look the same as water?
Yes.
Yeah, they do. Okay. Salt is a solid that dissolved into that water. Salt as a solid and liquid as water. Isn't that 2 phases? Why is that homogeneous?
Soluble?
the solid dissolved into the water. Okay? Which then meant I no longer see the solid. I only see one phase. So a lot of this comes down to what we can see. If I see one phase, homogeneous. If I see multiple phases, heterogeneous.
Are you talking about visually be able to, so?
Yeah, a lot of
when
it
you
is
can see-
visual.
When you can see sand inside water, then it's.
So let's take another solid and add it to water. Sand. Take sand and add that to water. What does the sand do? Sinks to the bottom. Can I still see the sand? Is it still a mixture? Yes. There's wet sand. It's still a mixture. We haven't even addressed that part of it. Okay. Do we still have two phases in that container? Yeah, we have a solid and a liquid. What kind of mixture is that? That is now a heterogeneous mixture. Okay. You ready for the big curveball one?
What about like ice in water?
Right? Ice in water. Right? That's an interesting one. What do you think? Homogeneous or heterogeneous? Heterogeneous because there are two different phases. Even though those phases are made up of the same substance, those are two different phases.
But even if it like eventually does absorb into.
Even if it does eventually all become one phase eventually, you're then looking at a different state. In that different state, it is now a homogeneous. So we could take a heterogeneous system and it eventually becomes homogeneous. Okay? My example for that one, anybody made Kool-Aid before? Take the little Kool-Aid packet, you pour it in the water, right? Okay. Loved Kool-Aid as a kid. Loved it so much that my parents were like, okay, we're going to limit your Kool-Aid content, but they didn't like saying no to us, apparently. So the way they limited our sugar intake with Kool-Aid said, you can have Kool-Aid, but you can't stir the water. So you can pour the Kool-Aid in, you can add the water on top, but you're not allowed to stir it. Which then meant you just had to sit there and watch. You could see it slowly dissolve in. You'd be like, it's not sugary enough yet. That shaking counts as stirring, in my family at least.
Science isn't
No.
generally called agitation.
Yeah, agitation. Eventually it would dissolve, and 2 or 3 days later you'd go back and you'd have Kool-Aid, but then you didn't want it. Right? So we can change the state. We can transition between heterogeneous and homogeneous, okay, depending on the timeline that we're looking at. So we want to remove time from our examples and look at an instant when we're looking at that particular case, what's going on. Okay. Here's the one I like asking about. Fog. Heterogeneous or homogeneous?
Homogeneous. You said
Fog.
Fog.
oh, wait, heterogeneous.
Fog. F-O-G.
Layers of it.
I know, that's a really hard one because no one here has seen fog. I was kind of kidding. Guys, give me some break. Okay. Fog. What do you think? Homogeneous or heterogeneous? Okay. If it was homogeneous, what happens when light hits it?
It'll go through.
It goes through.
Evenly.
Why does it not go through evenly in the case of fog? There's two different phases. There's actually solid, or not solid, liquid water droplets that are small enough that they're floating in the air. What happens when the light impacts it? It reflects, and that's why we can't see through fog. It's actually a heterogeneous system. Kind of neat, in my opinion at least. Pure substances, on our flip of it. These are chemically linked. Okay? Well, how many people, this is your first chemistry class? Okay, so I was expecting a little bit more hands on it. How many people can take a lower level chemistry class at the community college? You can't. This is the lowest chemistry class we got. Okay, so this is your intro to chemistry. And we are using, in the second lecture, defining pure substance with the word the course is all about. By the end of this course, you should understand chemistry. But on day 2, we are using that word to define something. Anybody see a bit of a problem there? Okay? It is not easy to grasp what is happening with a pure substance Because the only way we know it's a pure substance is by understanding the chemistry linkage. Okay? So the pure substance does become a little bit more difficult to manipulate, and that's why we can try and subdivide that out into our compounds and elements. Okay? An element is only one type for our pure substance. We conveniently have a list of elements known as our periodic table. So if I look only at a substance that has only Cr in it, that is now a pure substance that is an element alone. What happens if I move into being a compound? I have to have at least two elements chemically linked to each other. Okay? So let's go through and look at a fun example of salt and water. Salt happens to be a combination of sodium with chloride. Water happens to be
H2O.
2 hydrogens and 1 oxygen. So if I look at a container of salt water, how do I know it's a mixture versus a pure substance? So you can reach into a container of salt water and say, salt.
You can distill it.
So we can chemically separate, or not chemically, we can do a physical separation. We can go through and work through that process, but that's not particularly easy.
Like boil the water.
Okay? We'd have to go through a separation technique. Okay? That extra separation technique is what allows us to call it a mixture. What if I wanted to separate hydrogen from oxygen? That's a lot more difficult. That doesn't require putting a pot on the stove to boil it. That requires putting thousands of volts in proper locations to cycle out and cause an internal chemical reaction to chemically cleave hydrogen from oxygen, because there's a chemical bond. Okay? So in all that process I just went through and described, I use the word chemical again. Okay? We're in a very dicey boat for that side of the branch for our pure substances this early in the semester. There isn't a whole lot we can do about that. Okay? So when you look at questions about that side, do the best that you can to separate. For the most part, what we're asking for are things that, and I hate this word, are obvious. We're trying to pull at real-world examples. I have salt water. Well, that's salt and water. I can physically separate those through boiling. Versus a gold bullion. Okay? Gold bullion is just gold. Okay? Since it's only gold, that ends up being an element. Kinda, sorta? So, let's take a look at our elements. We want to come up with some way to subdivide and break these down. So in our initial investigations, we classified things as metals and nonmetals. Okay? So our metals, what do you think we got first up top? What image do you see up there? What do you think those are? Metals or nonmetals?
Metals.
Those are all metals. What characteristics do you see at those?
They're shiny. They're
Shiny. They're lustrous. Their
Solids.
colors are what?
or, sorry, it's colorful or it's silver and gold or whatever.
So we see a lot of silver kind of colors coming out of it. Some of them get a little bit weird with some crazy colors. So they were lustrous. Most tended to be silver. What else do we have?
Most to be hard.
Hard. Okay. They're hard because they are dense. Yeah, keep going. We already talked about compressed. They can be compressed. No, because they are solids. Most of our metals are solids. Okay, they tend to be shiny. Okay. The silver color is an important observation, and most are silver, but it does kind of run all over the place. Malleability, what does that mean?
You can like change the form of it.
You can change the form. You can hit it with a hammer and it doesn't shatter into a million pieces, it just kind of deforms. Okay? Conducts heat and electricity. That means when I light a match underneath my metal pot, what happens to the heat?
Transfers to the metal.
It transfers up through the metal and into the water I'm trying to boil to make my pasta. Okay? If I had instead, let's do that right now. If I instead used not a metal, but I had used a non-metal, say like carbon, okay, and all of my pots were made out of carbon, when I add heat to the bottom of the carbon, what happens? Okay. Let's not think about the disintegration of the carbon quite yet. What happens to the heat? Does it pass through?
No, it's absorbed.
No, it gets absorbed to break apart the individual carbon molecules. That's because nonmetals do not conduct heat. Okay? They are non-conductors of heat and ultimately electricity. Okay? We've got density, melting points. What is a melting point?
Transferring from solids to liquids.
Okay? Something is under intense heat, it melts. I like the intense heat part. I don't understand the melt part because that's a word used in the question to begin with.
Molecules start to become not fixed.
Okay? Molecules start to become not fixed. We have two words that we can use for this. It's the transition between
Phases.
solids and liquids. It's our phase transition between the solid and the liquid. It's not that you're wrong. You're absolutely right. Okay? But we want that solid to liquid transition. Does it require an intense heat?
Yes.
For some, good save. Okay, what is the melting point of ice?
32 degrees.
0 degrees Celsius or 32 degrees Fahrenheit. That's an intense heat. Yeah, that's why when we go into the, our freezer, we're like, ooh, I need to take off all some clothes because this is way too hot in my freezer. Okay? It's enough energy to break those forces. Okay? It's not necessarily an intense heat. Okay? Our metals tend to react with nonmetals. When we look at our nonmetals, most are solids or gases. Okay? And that's always a fun thing. Most things are two things. That's not really helpful. Most humans are male and female. Why don't you just get rid of the most and say we primarily have to deal with male and female?
Because of the sum.
Okay. Well, we don't need a sum. Why use the word most?
There's not some that are liquids.
Yeah, but we're saying two things. Most is just a weird word choice here. Whereas here, when we say most solids, it's really replying to most. When we look at our solids and gases here on our nonmetals, it splits roughly 50-50 between those two. Half of them are solids, half of them are gases. And even that, most are actually gases. Okay? Dull, they aren't shiny. Okay? They're brittle. When I hit them with a hammer, they shatter. Think about charcoal. Okay? Think about your bones. Okay? Brittle. They don't conduct electricity. They've got relatively low densities, low melting points. Okay? And they react with everything. Okay? As a general trend. Okay? Well, what if I have something that is very shiny but doesn't conduct electricity?
Non-metal.
Well, if it's very shiny, that means it's got luster. That would be a metal. But it doesn't conduct electricity. That's non-metal. So how does it fit? It's got characteristics of both. It's some kind of mixture between. That's where we invent the term metalloids. All right, and we got some images up here of metalloids. Those aren't particularly fun to look at because you look at those and those look an awful lot like our metals. Okay? But a lot of the other properties that we can't physically see are what separate them into non-metal type characteristics, like their abilities to conduct electricity and heat. Okay? What's that? Where's gold? Oh yeah, gold is a metal. Gold fits really cleanly actually on the metal side. Okay? It conducts heat and electricity very well. Okay? It is very malleable. It's very shiny. It's also a solid. With a relatively high melting point. Okay? So gold does fit very cleanly on the metals. Well, we've got a periodic table that organizes all of our elements, right? It'd be kind of nice if we had a way of being able to find our metals, nonmetals, and our metalloids. How do we do that?
Can you repeat that?
We got a periodic table that has all of our elements on it. It would be nice if we could look at that periodic table and be like, boom, you're a metal.
You can't.
There is.
You can't. There's a line.
Oh yeah, there's a system.
There's a system, there's an organization behind our periodic table?
Yes.
Oh, there's a line, a little zigzag thing coming down through the middle or on the right-hand side. Okay. Based off of that zigzag, what happens?
Left is metals, and in between the red ones and the line are metalloids, and the red ones are gases.
There's my red. Did I get my tier? I think I got my tier right. So we've got our metals, which are located on which side of that line? Left. Our nonmetals, where? Right-hand side of that line. Our metalloids had properties of both. Where might we expect to find the metalloids?
On the far right.
On the line. Okay. Is it perfect?
No.
No, which is often why I actually don't test on metalloids. Okay. Because you'd have to go through and memorize which ones were metalloids. But we have, for the largest part, everything on the left-hand side is a metal. Everything on the right-hand side of that zigzag is a nonmetal. So cool. We have a way to classify that information. What other information is stashed on the periodic table on the wall but is not on the one up here?
On the wall, you can tell by the symbols are written.
What do you mean? Elaborate.
One's shaded and one's not.
Okay. So what he has observed is that Charles, right?
Yeah.
Good. Sorry. I'm just proud of myself for that. Notice that some of those are colored in and some of them are not. Okay, so there's a difference. Not only is it shaded and not shaded, but what else do we see up there?
Different colors.
Some are red, some are blue. God, I wish I knew what those things meant. What I could do is look for the fine print, and in the fine print, what does it tell me? Black is solid. Anything that is a black letter is a solid. Anything that's red is a gas. Blue, liquid, they call it outlined, but Charles was saying white, which is fine. Synthetically prepared. Synthetically prepared because we had to make it. Those atoms are so huge that they do not exist naturally. We literally have to smash things together to say stay. Okay. And believe it or not, the process of saying stay breaks them apart.
So they don't.
That is how unstable they are.
How do they even become an element?
By atom smashing. Really, I blame physicists and mathematicians that said, I don't think there's enough elements, I'm going to make more. Remember that egotistical maniac kind of thing? It said, there aren't enough things to memorize, I'm going to make more things to memorize.
I can do it better.
Poof! I made more things to memorize, but they weren't any better because they just fell apart.
Were there any like synthetic elements that were actually applicable in like everyday use?
Everyday use, no. Some of them, I want to say americium is used in smoke detectors. I'm not positive on that one, but most of those are so fleeting in lifespan they just disappear.
Why even have them?
Why have them?
Because they
You just spent $1 million to make something. Yes, it may have died and disappeared right away, but you just spent $1 million to make it. Are you just going to be like, no one needs to know about that? That's why they're up there. Okay? Look to the table, 3.4 for properties. These are all the symbols. Notice that we don't have the names, but we've already talked about some. Gold. Mentioned carbon. Okay? How do we know the names to match the symbols?
Study, memorization.
You have to memorize it. Okay? There's only 118 things there. Can't be that bad. Just swing away. Don't do that, please. Check out Canvas, Files, Helpful Chem Stuff, I believe is actually what the folder is called, and within it, it says Elements for Memory. We cut that 118 down to 40-ish. It's roughly the first 4 rows. 1, 2, 3, 4. The first 4 rows you should nail down, and then it's kind of spotty here and there after that. Okay? Get those memorized. Yes, you will be tested on those. And with that, I have talked way too long.